We are beginning our section on rational expressions, and before we start that, we need to define what a rational number is. A rational number is any number that can be expressed as a fraction. So all whole numbers, all integers, all fractions. Any terminating decimal can be written as a fraction. Any repeating decimal can be written as fractions. So those are all rational numbers. So for example, as I said, any number that can be expressed as a fraction. So 3/4 is a fraction. 0.25, that's equivalent to 1/4, that is a fraction, a rational number. -7/3. You can have improper fractions, still considered a rational number. That would give you a repeating decimal. Your whole numbers, like 8 could be 16 divided by 2, 0, any negative integer as well is also rational. Now on page 351 of your textbook, there are two lists. One has expressions that are rational, and the second list has expressions that are not rational. So if you take a look through those, you can kind of compare them. And what a rational expression is, it's a sum difference product quotient of polynomials. And all variables must have exponents that are whole numbers. You can't have any square roots because that's really an exponent of 1/2. And your denominator can't be equal to 0. If you try dividing by 0, it's undefined. So we need to make sure we do something called stating restrictions as we go along, but that will come up in a moment or two. Okay, so really a rational expression is a quotient, the division of polynomial expressions. All your variables must have exponents that are whole numbers. So if you look at the examples of things that are not rational, they often do have fraction exponents or the square root on the variable. And the other thing we need to consider is that your denominator can't equal 0, so we're going to do something called stating restrictions. Now we're going to simplify here. Part A says 12 divided by 8. Now that's just actually an improper fraction that we've dealt with earlier on in our math career. What we would do is put that in lowest terms. And to put that in lowest terms, I'm noticing that 12 is divisible by 4 and 8 is divisible by 4. So we're really dividing the 12 by 4, and that, when 12 gets divided by 4, leaves me with 3. And when 8 gets divided by 4, it leaves me with a 2. So my simplified form of 12 over 8 is actually 3 over 2. Okay, moving along here, if I have an x squared divided by x, the rule is the bases are the same and I'm dividing, so I can subtract those exponents. 2 take away 1 is just 1, and that gives me x to the 1. Another way you can think of that is you have an x times an x squared is just x times x, divided by an x. This x reduces with that x, leaving you with just an x. Okay, now the reason I showed that is because that becomes helpful when we do more complicated simplifying of rational expressions. Okay, so now we have a monomial divided by a monomial in part C. We're going to treat it like a 9 divided by 3. The 9 divided by 3 could reduce. 9 can divide by 3 3 times. 3 divides by 3 once. So the 9 becomes a 3, the 3 becomes a 1. And then as far as the x's go, I've got 4 x's on the top and 1 on the bottom. It's going to be 4 take away 1, or x to the 3. So this is going to equal a 3x to the 3. And then on the bottom we would just have a 1, but we would normally just write that in simplified form as 3x cubed. Okay, now D looks a little strange. Like, why would I leave it as 6 plus 9 and then divide by 3? There's a couple ways we can tackle this. Normally Bedmas would say, let's put this together. 6 plus 9, that's going to give us 15. And then 15 divided by 3 is equal to a 5. But what I want to show you here with this one, okay, we're leading into more complicated examples. So we're just starting with numbers which are more simple. We know the answer should be 5 based on what we've done here. Now that 3 on the bottom, that is actually dividing both the 6 and the 9. So you can treat it as dividing both. If I do 6 divided by 3, so I'm going to go here with yellow, 6 divided by 3 is actually equal to 2, and then plus, and if we have 9 divided by 3, we get 3. And then 2 plus 3 is also equal to 5. So that gives us a second way to do that question. Now, the correlation here is when I look at part E. Do you see that I have something plus something else, and it's divided by a monomial, just like part D was, only I have x's? Well, I can't put the x cubed and the x squared together like I did over here with the 15. I can't do that because they're not like terms. But what I can do is what I did in the yellow, that x squared has to divide both of those pieces. So if you want to write it as an extra step, that x cubed has to divide the x, or the x squared divides the x cubed, plus we're going to have the x squared being divided by x squared. Okay, now some of you will be able to do that step in your head. You don't have to write that step in, but if you need to, it might help you stay organized. If I have x cubed plus divided by x squared, that's going to be x. And then we have our plus, and x squared divided by x squared. Well, anything divided by itself is just a 1. Now you could use your exponent rules. 2 take away 2 would be a 0, and x to the exponent 0 we know is actually just a 1 as well. So that gives you an expression of x plus 1 when you simplify it. Okay, so again, we're looking at a simple example and then extrapolating that to a more complicated example. If I have 4 divided by 4 plus 5, I know that I could add those together. So I'm going to have 4 divided by 9. Now that does not simplify any further. I cannot find a number that divides both 4 and 9 that goes evenly. So when I look at x and x plus 5, notice I did not, in the previous example, I did not cancel out or divide out the 4 and the 4. They don't reduce. Same thing here, I cannot reduce that x, and that's a common mistake that people make. So here's a numerical example of why that doesn't work. So this already is in its simplified form. I cannot make that any simpler than I already have. All right, let's take a look at part H here. Now, again, more complicated. However, what I'm noticing on the top is that polynomial could be common factored. There's a common factor of 2 there. So I'm going to pull 2 out, and it leaves me with a 2x plus 1. And on the bottom, I can common factor a 6. A 6 comes out of both of those, and that leaves me with a 2x plus 1. Now, you'll notice I have a thing on the top that's identical to the thing on the bottom, and I've got straight up multiplying and dividing. Everything's factored. I've got a 2 times the bracket 2x plus 1, and that's divided by 6 times 2x plus 1. So since I'm straight up multiplying and dividing here, that 2x plus 1 will reduce with the 2x plus 1 on the bottom. And that leaves me with 2 over 6, which in lowest terms is 1 over 3. Okay, try that with part I. See if you can common factor top and bottom, and then see if there are factors. So over here we had a factor of 2x plus 1 and a factor of 2x plus 1. See if there are any factors that are the same that you can reduce. And similarly, try that with J. See if there are any factors, if you can factor top and factor bottom, and then see if there are any factors that are the same. And if there are, you can reduce them. Put the video on pause, try it, and then play again. Okay, on the top, I'm noticing I could divide both by 8 and by x squared. So 8x squared is common, leaves me with an x plus 5. And on the bottom, I'm noticing that 8x cubed is common, and that leaves me with an x and a plus 5. So I have lots of factors here that are the same. I have an x plus 5, which would reduce with an x plus 5. So I'm crossing those out. X plus 5 divided by x plus 5 is just equal to 1. I also have an 8, a factor of 8, dividing a factor of 8. So what I'm left with is an x cubed divided by an x to the 3. Now, if I think of my exponent rules, that's going to give me x to the negative 1, which leaves an x on the bottom. Or think of this as 2x's multiplied on the top and 3x's being multiplied on the bottom. The 2 on the top will reduce with 2 on the bottom, leaving you with only 1 left on the bottom. So what we have left on the top is a 1 times 1 times 1, or just 1. And on the bottom you've got 1 times x to the 1 times 1, or just an x. Okay, the last example here, common factor at the top, I have 4 common, leaves me with an x plus 2. On the bottom I have a simple trinomial, two numbers that add to -3 and multiply to -10 would be an x minus 5 and an x plus 2. That's a plus 2. Oops. Okay, and then if I work from there, I notice that I have a factor of x plus 2 and a factor of x plus 2, top and a bottom. They cancel each other out. Leaves me with a 4 times 1 on the top and an x minus 5 on the bottom. And there's nothing further that I can reduce. So that's simplifying irrational expressions, part A.